Gen Chem students, my awesome night class, which is now, for the last time, going to be online. Well, today we're going to be doing titrations, and essentially a titration is simply neutralizing an acid and a base by mixing them together. And typically, you will either have an acid or a base added to a beaker, and then the other component will be added to a burette. The burette is what is used to add dropwise one solution into the other solution. And the key for a titration is normally to neutralize the acid and base by mixing them together. And you will usually see the end of a titration by an indicator, which is an additional compound that is added to basically either change color, turn the solution a different color, or make the solution go colorless to signify when you should no longer be adding any more solution from your burette. Now, the key points for an actual titration, should you ever do one actually in lab, would be the equivalence point and the end point. The equivalence point is essentially the point in a titration where the moles of base that you added is enough to neutralize all the starting moles of acid in your beaker, or the point where you added enough acid from your burette to neutralize all the base in your beaker, depending on where you have each located. Now, the end point is slightly different. That is theoretically one drop or half a drop past the equivalence point. Effectively, you have reached the equivalence point when all your acid and base are neutralized. But in order to activate your indicator, you add one more drop, and at that point, you reach the end point, which is when the indicator tells you that you have reached the end of your titration. The indicator might change the solution from one color to another. It might go from colorless to colorful, or it might just go from colorful to colorless. Depends on the situation you're working with. Now then, let's actually get into using the math of titrations. One situation is where you might want to standardize a solution of potassium hydroxide. Standardization basically means you're going to neutralize that solution in order to determine its concentration. And here is the following word problem. A beaker is filled with 50 milliliters of 2.750 molar nitrous acid. A potassium hydroxide solution of unknown concentration is added dropwise. Upon addition of 20 milliliters of the KOH solution, the indicator signals the end of the titration. What is the concentration of the potassium hydroxide solution? Well, in this case, we have our acid of known concentration and known volume in our beaker, and we are adding dropwise potassium hydroxide solution from the burette. Something to note about the reaction of nitrous acid and potassium hydroxide is that it is a 1-to-1 mole ratio. We'll get into different situations later, but it's just key to know that since it is a 1-to-1 ratio, something nice is going to happen. Well, let's start out with what we know from the word problem. We know that essentially we started out with 50 milliliters of a 2.750 molar nitrous acid solution. And in order to reach true neutralization or full titration, we had to add 20 milliliters of our KOH solution. So the first thing we can do is simply calculate the moles of acid we start out with. And that's effectively just taking the concentration of the acid multiplied by the volume in liters of how much we start out with. So 2.750 times 0.05 will give us 0.1375 or 0.1375 moles of our HNO2 solution. Now, next thing we can do is calculate the moles of base that we would need to have added to reach the equivalence point. Since our acid-base chemical equation is 1-to-1, this is pretty simple. In order to reach the equivalence point, we need to add just as many moles of our base as what we started out with our acid. So if we started out with 0.1375 moles of acid, we're going to need to add 0.1375 moles of base to reach the equivalence point. Now, cool. We know how many moles of our base we actually did add, and we know what was the volume we added. The volume of the base that we added was that 20 milliliters from the burette. So, to calculate the concentration for our base, to standardize our base, that is going to simply be the 0.1375 moles of KOH that was added divided by the volume it was in, or essentially those 20 milliliters, or 0.02 liters. And that's going to give us a concentration of 6.875 molar KOH. So that would be an example of standardizing a solution. Now, after you standardize a solution, you can use that same solution to determine the concentration of other acids, which is what we're going to do. Now, we can take, for determining the molarity of an unknown, or in this case, unknown acids, here are the following two situations we're going to work through. One situation is where the acid of unknown concentration is acetic acid, and then the second situation is oxalic acid. Now, acetic acid, that is a monoprotic acid, which means it only has one acidic hydrogen to lose in order to be fully neutralized. Effectively, that means that with a monobasic base like KOH, which only has one unit of OH, the molemole ratio of acetic acid to potassium hydroxide is going to again be 1-to-1. For oxalic acid, to completely neutralize oxalic acid, you would need to strip away both of its acidic hydrogens. So that means that it would be a 1-to-2 mole ratio of acid to base. We'll work on that one later though. Starting out with the monoprotic situation, here's the word problem. A beaker is filled with 110 milliliters of acetic acid solution. Titrate with the standardized 6.875 molar KOH solution from the prior run. After the addition of 80 milliliters of the potassium hydroxide solution, the indicator signals the end of the titration. Determine the concentration of the acetic acid solution. Well, it's going to be similar to how we solved the previous problem, except we're starting from a different point, which would be the base. In this case, we should determine, always start out with determining what you know from the word problem. What we do know is that we needed 80 milliliters of our 6.875 molar KOH solution to reach the equivalence point or end point of our acetic acid solution mixture. Let me rephrase that. We needed 80 milliliters of our 6.875 molar potassium hydroxide solution to neutralize 110 milliliters of our acetic acid solution. So let's first determine the moles of base that was actually added in order to neutralize our acid. And that's pretty straightforward. We have our molarity of 6.875 moles per liter of KOH. Let's times that by our 80 milliliters or 0.8 liters in order to determine the moles of base we added. In this case, we added 0.55 00 moles of KOH. So now the next thing to determine is what is the moles of acid that was neutralized in order to reach the equivalence point, or what were the moles of acid we originally started out with before we started titrating? Well, this reaction is a 1-to-1 ratio. Therefore, if we needed to add 0.55 moles of KOH to neutralize our acid, then we started out with 0.5500 moles of acetic acid. Therefore, moving on, basically, if we now know the amount of moles of acid we started out with, which was 0.55 moles of acetic acid, and we know that the original volume of just that portion of just the acid was 110 milliliters, then to calculate the concentration, it would simply be our 0.55 moles of acetic acid divided by the 110 milliliters, or 0.110 liters, which would give us a value of 5 molars. So, cool. We effectively have 5 molar. We can determine that our concentration of acetic acid was actually 5 molars. Now let's take a very similar situation where we're working with the same numbers in the word problem, but we're dealing with a diprotic acid. That means that for every 1 mole of acid we're neutralizing, it's going to need 2 moles of base, or 2 moles of KOH in this situation. So the word problem is still the same. It's a beaker that is filled with 110 milliliters of our acid, in this case oxalic acid, and you titrate it with our 6.875 molar KOH solution. And again, it took 80 milliliters to reach the equivalence point, or technically the end point, such that our indicator told us we were done. Now we're going to calculate the concentration of our oxalic acid solution. And pretty straightforward. The first calculation is the exact same because calculating the moles of base, well, our concentration of base was 6.875 and we used 0.08 liters. That's what was added from the burette. So those two numbers multiplied together will still be 0.55 moles KOH. Now here's the trick though. Our moles of acid and our moles of base are not 1-to-1. It takes 2 moles of our base to react and neutralize 1 mole of our acid, or fully neutralize 1 mole of our diprotic acid. Therefore, in order to determine the moles of acid that was fully reacted by the time we reach the equivalence point, we're going to need to use this mole ratio, which is 0.55 moles of our base times 1 mole of our acid divided by 2 moles of our base. And that will give us 0.275 moles of our sulfuric acid, of our oxalic acid. That's the key to note, is that with acid and base reactions, it's not always going to be 1-to-1. So you should know how to recognize those situations and use a mole-to-mole ratio to correctly determine the amount of moles of your acid you actually did neutralize. Now then, we did determine what that number was, which was 0.2750 moles of oxalic acid. So that is the moles of our acid from our solution before we started titrating it. So the volume of that acid solution before we added any base was again 110 milliliters, or 0.11 liters. So to calculate that number, to calculate the concentration of our oxalic acid solution, of our diprotic acid solution, it's just going to be the moles of 2.75 divided by our volume of 0.11 liters, and that will give us a concentration of 2.5 molars oxalic acid. And, well, yeah, there you go. That would essentially be how to determine concentrations of acid or bases from acids or bases by neutralizing them through a titration. And this was an example of a diprotic acid where the acid to base ratio was not 1:1. So, as a bonus for you guys, working with the same volumes, same concentrations, same numbers, but in this case, you're going to be working with a triprotic acid, or specifically phosphoric acid, which requires 3 moles of base to react and neutralize 1 mole of the acid. So, work through this problem and submit your answer for a little bonus. And that is truthfully the conclusion of our lessons for General Chem. And well, I gotta say, not bad for a global pandemic, if I do say so myself. So, it has been a pleasure teaching you guys beautiful general chemistry. I loved the night class, and I have certainly been very proud of the wonderful work you have been submitting, even since we converted to an online format. So, here is to hopefully seeing you guys in Gen Chem 2, online or otherwise. Have a great end of this semester. That's all.